Hello, Algebra 1 students! Today we are getting into Chapter 5, which is all about linear functions. And to be honest with you, I think that this is my favorite part of algebra here that I get to teach you. We get to learn about graphing lines in different ways, since mostly we've been learning how to do it from a table. We get to learn about different parts of these lines, things like slope and intercepts. And we get to do all these cool things with these lines. And a lot of this stuff carries over into other things that we're going to continue doing here into algebra. So we have a big chapter ahead of us with lots of different things to it, but a lot of things that I think we're going to be revisiting as we go through. So hopefully it makes sense as we go through, but as always, ask me questions if you need to. Today, we're going to be talking about identifying linear functions. So I feel like we've got a lot to cover in this video, so let's see how far we can get. But we already understand our functions. Today, we're going to talk about linear functions. So let's go ahead. So our objectives are I can identify linear functions and linear equations. And I can graph linear functions that represent real-world situations and give their domain and range. So we've already talked about what makes a function. I think, though, that this is going to be really helpful for those who are still struggling on identifying functions, as well as we know how to identify domain and range. So kind of a review on things we've learned here, but a little bit different as we continue on. So here are some key ideas that they start talking about. They talk about why learn this. Well, they say linear function can describe many real-world situations, such as distance traveled at a constant speed. Most people believe that there is no speed limit on the German Autobahn. However, many stretches have a speed limit of 120 kilometers per hour. If a car travels consistently at this speed, we can make the equation y equals 120x, given the number of kilometers y that the car can travel in x hours. So they graphed it and show that kind of relationship over here. The graph represents a function because each domain is paired with exactly one y. So remember, our functions are described as this, is that each x value or each domain should have one unique y value. I think some people were getting confused on the flip side of that. It's okay that, x is 1 and it's 120, but I can't have x is 1 and it also equal 240. That's not going to work for your y. So notice that the graph is a straight line. Now it's a diagonal straight line. A function whose graph forms a straight line is called a linear function. So because there's no weird curves in it, it doesn't go down, this is considered a linear function, okay? So a lot of it comes down to understanding the graph as well. So let's go ahead and talk about the first example. So as identify whether each graph represents a function. Explain if the graph does represent a function, is the function linear? So we talked about graphs prior and understanding if a graph is a function. Remember, there's a thing called a vertical line test. So this vertical line test will tell me if it's a function, but it doesn't necessarily tell me if it's linear. So let's go ahead and take a look at the first one here. And I'm just bringing brackets so that's a little easier to break it up. So A here, if I were to create a vertical line anywhere on here, it's only going to cross this graph or this red line once. So that passes the vertical line test, which means it's a function. So it is a function. And then they talked about, is it linear? Remember down here, they said that a function whose graph forms a straight line is a linear function. And this does create a straight line. It is a function, and it is linear. All right, B. Again, we can use that vertical line test to test if it's a function. So if I were creating lines, vertically here, it looks like it's only ever going to pass the red line once, which means it is a function. But since this graph curves here and it's not a straight line, I would say it's a function, but not linear. All right. Now this one's tricky because the C here, because if I created a vertical line test to decide if it's a function, well, it is not a function. So it's not a function. But it is a straight line. But because it's not a function, I can't even talk that it's a linear function. So no function just means none of it. I can't even determine, that it's a linear function. So even though it is a straight line, it's not a function, so I can't call it a linear function. So the next part says you can sometimes identify a linear function by looking at a table or a list of ordered pairs. In a linear function, a constant change in x corresponds to a constant change in y. So they show this constant change, which we're going to talk a little bit more about as we continue through. So if they're looking at this graph here, the x's from each x as they go up or go down here, they're adding 1. So -2 plus 1 is -1. Same thing, then over on the y side, as they go down the list, it's going down or subtracting by 3 each time. It says in this table, a constant rate of change of +1 in x coordinate to a constant rate of change of -3 in y, these points satisfy a linear equation. So because they are consistent, I can call this a linear function. And if I were to graph it out, it would look something like this. On the other side here, in this table, my x's are still going up by 1 on this side, but if you notice on the y, it goes down by 3, then it goes down by 1, then it goes up by 1, and then goes down or up by 3. And so what happens on this side, it says that in this table, a constant rate of +1 in x does not correspond to a constant change in y. These do not satisfy a linear function. So again, this is similar to the second one we looked at where it's more of a u. It's a function, but it's not a linear function because the y isn't consistent. It's not going up by one rule. The rule keeps changing. So we're going to take a look at some examples like that. I'm going to grab some water here. So it says, tell whether each set of ordered pairs satisfy a linear function and explain. So I think the best way might be to look at that table. So with my coordinate points, my x is 2, y is 4, 5, 3, 8, 2, 11, 1. So I want to think about what kind of changes are happening between each one. Well, from 2 to 5, that looks like +3. From 5 to 8 is +3. From 8 to 11 is +3. So that's fine. We just got to make sure that the y has a constant rate. 4 to 3 is -1. 3 to 2 is -1. 2 to 1 is -1. So because these are all the same on both sides here, this change each time, I get to decide that this is a linear function. So tell whether each set of ordered pairs satisfies a linear function and explain. Yes, it is linear. Because x and y have since both x and y have constant rates of change, meaning they're being consistent whether I'm adding or subtracting. So I'm going to do the same thing for B. Let's create a table, x and y. So in the first one, -10, 10, -5, 4, 0, 2, and 5, 0. All right, I want to see what the patterns are. So from, looks like negative 10 and negative 5 is plus positive 5. It seems to be that's the same thing as we continue on. So let's see, does y have a constant? Well, 10 to 4 means I'm subtracting 6. 4 to 2 is subtracting 2. And 2 to 0 is subtracting 2. So these aren't the same. I'm not always subtracting 6 or always subtracting 2. And so in this case, since this is not consistent, I'd say not a linear function. And you could write why it's not a linear function, saying that the y, it does not have a constant rate of change. So again, you're looking for those patterns. So as long as the pattern stays consistent, it's a linear function. If it doesn't, then it's not a linear function. All right. So another way to determine whether a function is linear is to look at its equation. A function is linear if it is described by a linear equation. A linear equation is any equation that can be written in standard form. I'm surprised we're already getting into standard form here. So here is what standard form looks like. It says ax plus by equals c, where a and c are real numbers and a and b are not both 0. Notice then when a linear equation is written in standard form, x and y both have exponents of 1. X and y are not multiplied together, and x and y do not appear in denominators, exponents, or radical signs. So you have some other things. For any 2 points, there's exactly one line that contains them both. This means that you need only 2 ordered pairs to graph a line. So I talked a lot about that as before when we're creating tables. You only really need 2 ordered pairs. I say 3 to 4 for your best explanation on how that graph goes, though. So let's go ahead and look at these. I'm just double checking how far we have. So this is tell whether each function is linear. If so, graph the function. Now they said if it can be written in standard form, which was this ax plus by equals, I think it was c. Yeah. If it can be written in this form, which I can move things around here and I can go y and I could subtract this x minus x equals 3. That would work because I have an x and a y. It's okay if that's a subtracting. Doesn't matter what order they're in. And the c obviously is going to be some kind of actual integer. Same with b and a. So yes, this would be considered a function. But also I want to show with a graph here. We're going to come up with a quick little graph. I only really need 2 points for it. So what if I plugged in 0 for x? Well, if I created a table and plugged in 0 for x, 0 plus 3 would give me 3 for my y. So I'd have the point 0, 3, which would be right here. And what if I plugged in 1? 1 plus 3 is 4. So then I have the point 1, 4. And from there, I can connect them together and form a line. And so yes, this would be a linear function, and I can double check that with my graph here. For b though, if you remember what kind of graph these create off the top, they're going to create a U-shaped graph. So I can't actually write this in standard form. It's not going to work because I can't have it to different exponents, because in here they say both x and y are to an exponent of 1. So right off the bat, by looking at this equation and understanding that if I were to graph it, it'd give me some sort of U shape, I know that this is not a linear function. All right. I don't think we can get to this last one, which is totally fine. we will talk about this more here in class. I think this is something we can definitely understand as we get to the homework without seeing this example. So I will see you then.